ustedes saben que el idioma que vamos a utilizar fundamentalmente es el inglés, por cortesía con el invitado principal, así que voy a leer unas palabras en inglés. Universidad de Santiago de Chile welcomes all speakers, authorities and attendees. We appreciate your interest in joining us today for the workshop Green Chemistry Research, Advancing Sustainable Practices in Chemical Research for Environmental Impact Reduction. To begin with, I would like to invite Dr. Alexis Aspe, Deputy Dean at the Faculty of Chemistry and Biology, to deliver the welcoming remarks. Please, Alexis.
Ok, muchas gracias a todos. Voy a hablar, ¿se escucha bien? Voy a hablar en español. Yes, I'm going to start in Spanish, okay? For a while. Thank you very much, everyone. Welcome to this workshop. And first of all, thanks to everyone. Y estimadas autoridades universitarias, invitados e invitadas, estimada comunidad universitaria académica de la Universidad de Santiago de Chile, querida Facultad de Química y Biología. Buenos días. En representación de la doctora Leonora Mendoza, decana de la Facultad de Química y Biología, y desde el Vicedecanato de Investigación y Postgrado, nos complace darle la bienvenida a este workshop. En esta oportunidad, nuestra universidad es la anfitriona de este evento, que busca generar conciencia en torno a la búsqueda de soluciones comprometidas con el cuidado del medio ambiente y del planeta. Una actividad que está en coherencia con el interés de la Universidad de Santiago de Chile, y en especial desde la Facultad de Química y Biología, en promover la ciencia sostenible y compartir las prácticas en torno a la química verde, principalmente porque creemos que sus principios debiesen ser parte de la cotidianeidad de nuestra universidad. En noviembre del año pasado, la Facultad de Química y Biología, a través del Departamento de Ciencias del Ambiente, firmó un acuerdo de entendimiento con la organización sin fines de lucro, Benign, para poder avanzar en estos desafíos medioambientales para las áreas experimentales de la química y la biología. En particular, en la enseñanza en torno a las competencias de la química verde y de la ciencia sostenible, desde su teoría y aplicación en las tareas de la investigación hasta el desarrollo de habilidades en el laboratorio, tanto en nuestra comunidad investigadora como estudiantil. Agradezco la presencia de nuestro invitado, el Dr. John Warner, por sus importantes aportes y participación al comité organizador, y a los conferencistas, la doctora Ilux Almodóvar, de la Facultad de Química y Biología de nuestra universidad, la doctora Paulina Pavés, de la Pontificia Universidad Católica de Chile, al doctor César Barrales, de la Universidad de Talca, y al señor Marco Rebolledo, de MER Chile, por su participación en este evento. No quiero dejar de mencionar también al Departamento de Relaciones Interuniversitarias e Internacionales de la Universidad de Santiago por su importante rol en esta actividad académica, así como también la presencia del Colegio Chileno de Químicos, de las empresas MER, Anamin Group y al grupo y equipo de profesionales de la Unidad de Desarrollo de Posgrado de nuestra facultad que han estado involucrados en la realización de este workshop. Por último, solo me queda desearles a todos y todas que tengan una muy buena jornada, que tengan muy buenos días. Muchas gracias.
Thank you very much, Dr. Alexis Aspe. I would like to mention that this activity has been coordinated jointly with the Faculty of Chemistry and Biology with the support of the Department of International and Inter-University Relationship, as Dr. Alexis said, and the organizing committee formed by Professors Angélica Fierro from Pontificia Universidad Católica de Chile, Gerald Zapata and Pablo Jaque from the University of Chile, Marco Rebolledo from MEC. The main aim of this event is to encourage the practice of green chemistry in universities so that it gradually becomes the only way we think and do chemistry. That is why we have specially invited Dr. John Warner, co-founder of this field, an extraordinarily inspiring person to whom we are deeply grateful for being here in person today. Taking advantage of this event, we are pleased to announce that the Faculty of Chemistry and Biology is honored to be the first in Chile to join the Green Chemistry Commitment Program. In this sense, we invite Dr. John Warner to speak what is this program about. Please, Dr. Warner.
Well, thank you very much, and I'm so honored to be here to speak with you. The way I want to describe the importance of the green chemistry commitment. Let's imagine we find 1,000 people working in sustainability. 900 of those 1,000 people are probably talking about why we should do sustainability. Okay, they talk about climate change, they talk about water pollution, ocean plastics, and things like that. Maybe 90 talk about what? UN SDGs, circular economy, but only 1 in 1,000 talk about how. And that's the field of green chemistry. But people can't do it without learning how to do it. That's why it's so important that people are signing the green chemistry committee, because we can't solve society's problems just by wanting to. We have to learn the skills. And so that's the wonderful opportunity here today. And so I congratulate the University of Santiago de Chile for being the signer, and thank you from the bottom of my heart for doing this. I'm so honored and pleased to be here to share this moment with you. Thank you.
Thank you very much.
Yeah.
Thank you very much. We ask you please to stand here to invite Dr. Alexis Aspe, who John will deliver the certificate that accrediting us as signers of the Green Chemistry Commitment Program. Please. Thank you very much. Continuing with our program, we have planned 4 presentations, a coffee break, and a poster session during the morning. After each presentation, there will be some minutes for questions. The first talk of this event is in charge of our special guest, Dr. John Warner, and is entitled Green Chemistry, the Missing Elements. Dr. Warner is a chemistry inventor who works to design and create commercial technologies inspired by nature, consistent with the principles of green chemistry. With over 300 patents, he has invented solutions for dozens of multinational corporations. His inventions have also served as the basis of several new companies. Dr. Warner is one of the co-founders of the field of green chemistry, articulating the 12 principles of green chemistry with Paul Anastas. He has received prestigious awards, some of them including the Presidential Award for Excellence in Science Mentoring, the August Wilhelm von Hoffmann Medal, and the Perkin Medal. Dr. Warner was also named one of the most influential people impacting the global chemical industries, and one of the 25 visionaries changing the world. He serves as Distinguished Professor of Green Chemistry at Monash University in Australia and Strategic Advisor for the Science, Engineering and Health Committee of IPA Victoria in Australia. Professor Warner received his Bachelor in Chemistry from UMass Boston and his PhD in Chemistry from Bristol University. After working at the Polaroid Corporation for nearly a decade, he then served as tenure professor at UMass Boston and Lowell Chemistry and Plastic Engineering. He co-founded the Warner Brock Institute, the Warner Babcock Institute for Green Chemistry with Jim Babcock, a research organization developing green chemistry technologies, and Beyond Benign with Amy Cannon, a non-profit dedicated to sustainability and green chemistry education. Dr. Warner, please, everything is ready for you.
exercise. It's my pleasure to be here. And trying to decide what to present today, what I decided to do is to try to give people an understanding of where did green chemistry come from? What is the history of green chemistry and what is it? You know, when I come to a group of people, I'm always amazed that people hear the word green and they hear the word chemistry and they say, oh, it must be this, it must be that. And then when I actually explain what it is, they go, oh, that's what it is. And so I want to really today, to celebrate signing the Green Chemistry Commitment, trying to give a personal journey of where does this come from. And look, it's now 2024. Chemistry is not a popular subject, okay? It's scary. I don't know if these buttons, oh, there we go. It's scary. It's the monster lurking underneath our bed. Most people in society think that chemistry is a terrible, dangerous thing. If people in society are talking about chemistry, it's usually not good. Open up the newspaper, turn on the radio, look on the internet. All we hear is, this is bad, this is scary, this is bad, this is toxic. Who would want to be a chemist today? You know, it's all bad. And it's like the game Whack-A-Mole. You know, where the thing comes up, you hit it, and it comes faster and faster and faster. Well, we chemists, we like our moles, right? The American Chemical Society's mascot is actually a mole. And so what we do is we find, okay, climate change, whack. Bisphenol A, whack. PFAS, whack. Nanoparticles, whack. Ocean plastic, and we're exhausted because, thank you, we're thinking, we start thinking about one issue. We say to ourselves, is this really serious or is this like hype? And we're not really sure, but before we can understand it, another issue comes, and then another issue comes. And if we chemists, if the only people that understand molecular structure and how molecular structure correlates to how a molecule behaves, if we're confused, what is the rest of the world doing? All right? So essentially, let's accept that there are materials and plastics that are endocrine disruptors, that there are technologies that contribute to climate change, that there are materials that are persistent and bioaccumulative, and there's molecules that cause cancer and things in plastic that cause, except that this does happen. We spend all the time saying, is this toxic? Is this dangerous? Should we ban this? What should we do? And I would argue that we're not asking the right question. The question that we should be asking is, why would a chemist make a material that is a carcinogen? No one wants it to be a carcinogen, so why do we do it? So maybe, instead of talking about how we make molecules, we should talk about how do we make chemists. All right. Now, I'm not a historian. I can't quote the history of chemistry, but I'm a chemist. Maybe if we look at my history, how did I become a chemist? Maybe there's something we can learn about this, okay? So my accent, if people understand English accents, I have a very distinct accent. I sound like I come from Boston, Massachusetts, okay? I sound like a Kennedy, okay? And so Quincy is the city just south of Boston, okay? And so my accent is very distinct for that. Quincy in the United States is a pretty nice city. 2 presidents of the United States are from that city, John Adams and John Quincy Adams, all right? And in my opinion, the greatest chemist who ever lived is R.E. Woodward, Robert Burns Woodward. He came from the city of Quincy. Robert Burns Woodward got the Nobel Prize for the synthesis of vitamin B12. But you can't get the Nobel Prize after you die. And 3 Nobel Prizes afterwards, synthetic methodologies, Woodward-Hoffman rules, and another, he would have gotten at least 3, maybe 4 Nobel Prizes if he lived long enough. So I consider him the greatest chemist that ever lived. And he was from my city, He actually came, he went to the same school that I went to, but I never heard of him as a student. You see, I'm not some child that grew up wanting to be a chemist, okay? I come from a huge Sicilian German family. I had 42 first cousins growing up within a 5-kilometer ratio. And we were carpenters, plumbers, electricians. We didn't know anything about college and university. That wasn't something that was part of our life, you know. Here is my high school. That's the room where chemistry was. That's probably where he went, but I didn't know anything about that. I did end up going to university, but I went to university at the University of Massachusetts, Boston, which at the time was the most affordable university in the United States. And I worked full-time as a construction worker, 40 hours a week, while going to undergraduate. But what I went to school for was for music. I was a musician, all right? But I played in a band. And the name of my band was, wait for it, The Elements. This had nothing to do with carbon, hydrogen, nitrogen. There's a Rubik's Cube, a glass ball. It was the late 70s. Those were our elements, okay? And we were okay. We were playing 3 nights a week at some interesting places. We had a recording contract. We were recording in the studio. Things seemed to be going well. When disaster happened, and the drummer of my band ended up getting cancer, and over the course of 6 months, he died. And all my whole life is around music, everything. And then when he passed away, I'm like, what am I gonna do? You know, my relationship to music changed. Now, at the University of Massachusetts, a music major still has to take a math class, still has to take a foreign language, still has to take a science class. Oh my goodness, I had to take a science class. I liked biology, mitosis, meiosis, genetics. That was kind of cool. And I love physics, astronomy, and subatomic particles. So I'm saying, should I take biology or should I take physics? Should I take biology? Should I take physics? And in a moment of inspiration, I added them up, divided by 2, then I'll take chemistry. Not because I was particularly interested in it, but I saw it as halfway between biology and physics. So here I am taking this required chemistry class, and a professor comes in one day, Professor Jean-Pierre Ansel. He looks at me, I'm a music major, he's not interested, but he goes to the student next to me, and he says to the student next to me, would you like to do research? I've just lost my friend, I'm wondering what I'm going to do. I heard that, I said, can I come? And I went into the research lab. And I have to tell you, when I got into the research lab, everything changed. Always in my life, I thought there were 2 types of people. There were artists and there were scientists. And because I was marginally okay at music, I must be an artist. But when I got into the chemistry research lab, and I found out that chemistry is more than just PV equals nRT, that chemistry, people design things, they create things, they make things. I said, I bet you, if you put this neurological device in my brain and put these electrodes, and I compose a piece of music on a piano and go bloop, 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 you see what the brain is doing. Or I drew a polymer or some molecule, then I bet you the same brain activity happens whether you're composing a piece of music or creating a molecule. That creativity is not art, is not science, it's something more human. And once I understood that, I could follow my passion, my creativity as a chemist. And so next thing you know, by the time I'm 18 years old, I've already published 5 papers in journals. And in fact, I made the cover of Celebrity magazine with Boy George. That's not a claim to fame, not as a musician. It's funny, this person with a really cool voice calls me on the phone and says, John Warner, we consider you Boston's best and brightest college graduate. We want to do a story on you. And I go, no. And I hung up the phone. I go to school the next day, and the chancellor of the university comes to the lab and he goes, you will go get your picture. And so here I am, hating life, surrounded by all these happy people, and I do this story about this kid who has synthesized over 100 molecules that have never existed in the world before, putting atoms in unique geometry that God never intended. And I'm reading this thing. I'm a chemist? How did that happen? Well, next thing you know, flotsam and jetsam, I find myself at Princeton University, working in cancer chemotherapy. Published like 16, 17 papers, but 12 of the papers that I published was on the synthesis of this molecule here that ended up being the drug Alimta, sold by the Eli Lilly company. It's one of the most successful solid tumor anti-cancer drugs so far in history. And so a lot of people worked on this. I played a small role, but I am the patent declaration signature on the patent is mine. And just to show the relationship between science and society, in 2002, I lost my mom to cancer. She was receiving the drug that I had helped design 15 years earlier. So this relationship between science and society has always been kind of interesting. If you go to the Princeton campus now in New Jersey, you see the chemistry building, this amazing chemistry building, is built entirely from the money they received from this one molecule that's the Eli Lilly's anti-cancer drug, okay? So I'm about to graduate Princeton, all right? 2 universities, I didn't apply, 2 universities asked me if I would be willing to be a professor at their university. So I said, okay, I'm gonna go to academia. I'm gonna be a professor of medicinal chemistry. Here's my lab. My dad came at graduation to see what this crazy son of his was doing. But I'm working in the lab one day and the telephone rings. And I answer it, and it's this person called Lloyd Taylor. He's a very famous polymer scientist that works at the Polaroid Corporation, you know, the instant photography company. There was a time when you had a device that took a picture, took a photograph, and you could not make a telephone call out of it. You know, there was a separate device. Okay? Right now people look at me, what, really? But Polaroid in the 1980s was the coolest place to be as an organic chemist. It was really cool. And so this guy brings me to lunch and he says to me, you know, I want you to come and head an exploratory research group at Polaroid. And I say, sir, I'm an academic. I'm going to be a medicinal chemist. He told me how much he wanted to pay me. I said, when do I start? And now I'm an industrial chemist. How did that happen? Polaroid, Edwin Land is one of the most famous inventors in U.S. history. Okay, he got the Perkin Medal in 1974. How cool is that? Then they gave it to me in 2014, so seriously, how cool can it be if I got it? But I found that I had this ability to do chemistry. It was very strange. And within 4 or 5 years at Polaroid, filed 40 patents in medical diagnostics and holography and all these things, and I started to invent. But you gotta ask yourself, what would a medicinal chemist do at a place like Polaroid? As a medicinal chemist, I'm usually working with molecules that float in water bags of cells at room temperature and ambient pressure, right? But industry is high temperatures, organic solvents, and so I said to myself, if you look at nature, the complexity of the molecules that nature makes is far more complex than what we can make. But how nature makes it is also better. Everything in cells and biology is at room temperature, water as a solvent, ambient pressure. And so I said, how is it, why is it that biology can do it? And I could talk for 2 hours about this. I'm going to give you the 1 sentence short thing. He came up with this concept called non-covalent derivatization. And I say that we humans, we have evolved our chemistry to focus on enthalpy, delta H. And we don't really think too much about entropy. Biology has evolved to focus on entropy, less than enthalpy. And by looking at non-covalent interactions, hydrogen bonds, pi interactions, lipophilic interactions, everything in biology is more governed by the non-covalent interactions than the covalent. And so I just started looking at these big manufacturing processes, and instead of looking at the covalent structure, looked at the non-covalent interactions and found, ooh, this is a way to change a lot of things. One of my inventions, Polaroid in the photographic industry, called Warner complexes. Okay, it's kind of strange to have a complex named after you, but Polaroid went to large-scale manufacturing. Now, in the United States, you can't just do that. You have to go to the Environmental Protection Agency and get permission to do this. So you have to get what's called a low volume exemption, a pre-manufacturing notification. This is back before the internet, so you fill boxes of paper and ship it down to Washington, D.C. So we did, and we waited, and we waited, and we waited. And the EPA was having a hard time. They said, small particles, what are you talking about? Molecular complexes, what are you, crazy? What are you, high? And so Polaroid put me on an airplane and sent me to Washington, D.C. It was the first time in my life I'd been on an airplane. I'm in Washington, D.C. I'm holding a briefcase of overhead transparencies. That was the technology back then. I'm a little bit scared, and I'm a little bit mad. And I go to the Office of Pollution Prevention and Toxics, this guy, Paul Anastas. Wait a minute. Remember the person that I followed into the research lab when I was a music major? It was him. I've known him since I was 11 years old. I went to UMass with him. In fact, I was playing in this really cool, like a Tower of Power funk band with his older brother. There's him on the saxophone, me on the keyboard. My older brother, I just want to make fun of him internationally. Look at his hair. And this guy here is in Las Vegas. One of the biggest, most successful acts in Las Vegas is the Legends of Rock, where people perform as other people at famous things. And so the person who plays Rod Stewart at this show is him. Has absolutely nothing to do with this talk. Okay? So anyways, I'm saying to Paul, wait a minute. Polaroid has been making these molecules with all these solvents, all this energy, and you're fine with that. I've come with a new technology that is aqueous, non-toxic, room temperature, and you're giving me a hard time because it's different. If I was doing the same thing, that's okay. But if I do something different, the EPA doesn't know how to handle something different. Isn't anything better for human health and the environment going to be different? All right? So I'm in Washington, D.C. I'm having this philosophical discussion, right? Thinking about the regulatory structures and the incentives in industry. And at exactly the same time, this is like 1991, 1992, at exactly the same time, my career at Polaroid is going amazing. I've gotten promotion after promotion, award after award. My head is this big. I am the greatest scientist who ever lived. And disaster hits again. And this time, I lose my 2-year-old son, John, to a birth defect. My son John was born with a disease called biliary atresia, where his liver was detached from his intestines and he couldn't metabolize water-insoluble nutrients. So he got surgery at birth, and at 2 years old, he died. Lying in bed the night of my son's funeral, I'm asking myself, I wonder if something I touched in the research lab somehow caused this birth defect. I wonder if, heaven forbid, something I got an award for caused this disease. I didn't feel like some amazing chemist. I thought there was something missing. Right? So now I'm thinking about it. There are books around that time coming out called Our Stolen Future, talking about the impact of human-built chemistry on this, on the environment, on humans. You know, here I've probably synthesized about 2,500 new molecules, not repeat syntheses. I, with my hands, have synthesized 2,500 new molecules. And I realized, never had a class in how do you predict whether something's toxic. Never had a class, how do you predict whether something might hurt the environment? How is it possible that I can be so successful as an industrial chemist and have no idea at the mechanistic level? I start looking, and turns out it's well known. Professional chemists are at risk of getting certain types of tumors, elevated breast cancer mortality among folks. Now that I'm looking, I get all of these information. Why is it that I had 4 years of undergraduate, 3.5 years of graduate school? I never had a conversation, never had a seminar, certainly never had a course that taught me how do I anticipate at the molecular level whether something I'm creating could hurt humans or the environment. Huh. So I start looking. Every year, just in the United States alone, not the world, just the United States, we graduate 15,000 undergraduates in chemistry every year. We graduate 3,000 master's degrees, 3,000 doctoral degrees. In 2004, more women started to become chemists than men. What could be more important to the field of chemistry and material science than understanding how to anticipate going wrong, making something that hurts humans or the environment? What course in any curriculum could be more important than that? And yet, to get a degree in chemistry, back then it was 0 universities in the world had any courses, any training on how do you anticipate this. All right? And so I'm looking at this and I'm saying, all right, this is bad, but there's hope. Why don't we start teaching chemists a little bit about this? And so when you ask yourself, why are there these things happening? This isn't a battle of good and evil. It's not like chemists are evil or industry is evil. For some strange reason, the field of chemistry and material sciences has evolved to not see this as part of our job. Imagine if I were to get a bunch of 10-year-old children, or CEOs of corporations, or PhD chemists and engineers, and I would show a bottle of some material and say, let's name the properties of this material. Someone is going to say solid, liquid, gas. Someone's going to say it boils at a certain temperature, it melts at a certain temperature. Maybe talk about the color or the viscosity or the electrical conductivity or the flexibility. We'll see all these lists of things. But in 2024, still today, it's unlikely that anyone would think, what is the toxicity of the material? What is the impact on the environment? For some strange reason, the world has evolved that the scientific discipline of understanding structure, activity, relationship has evolved that that's not part of what it means to be a chemist. And so Paul Anastas at the EPA and me as an industrial chemist realized that the world didn't need a philosophy, the world didn't need a social movement, the world needed a mechanistic science. When you learn chemistry, there's a textbook called analytical chemistry. There's a textbook called organic chemistry and physical chemistry. Now when someone says to me, I'm an organic chemist, like, what does that mean? You never do any physical chemistry, you never do any, obviously you do a little bit of everything. The word organic and physical is just how we teach chemistry. That doesn't define people. To be a functioning scientist, you gotta do it all. But if there isn't a textbook called green chemistry, if there's not training in green chemistry, then we have exactly the situation we have now. So we needed a science in the same way so that we would have journals, we would have textbooks, we'd have classes, we'd have conferences, we'd have workshops. That's the vision of green chemistry. Now here we are, 26, 28 years later, and there are now 12 international journals of green chemistry. At last count, there are 65 textbooks of green chemistry. Bless you. Every week, somewhere in the world, there's a green chemistry workshop or conference, and that's the point. Rise at the same level of discipline as anything else. And so green chemistry came, and I'm so honored to be seen as the figurehead, the co-founder, but the truth is that there are thousands of people, some of them in this room right now, that are leading green chemistry. I'm convenient figurehead, or let's say, but it's not about me, it's about the thousands of people that are changing the world doing green chemistry. I'm as shocked as anybody to find this book has been translated to over 15 different languages. At last count, I've been to like 77 countries. So Chile is the 77th country that I've been invited to give some talk about green chemistry. And so, but it's all the people here that are making it happen. And so it's just, but what I'm proud of most is the principles of green chemistry. Because what the principles of green chemistry is connect the why and the what with the how. So these things are mechanisms. It talks about activation energy levels, reaction coordinate diagrams, hydrogen bonding, things like that. And so it's how does one look at climate change and say, what mechanisms at the molecular level contribute to that? When someone says, well, what about carcinogenicity? Well, what are the mechanisms? So how do we translate these very important global problems to this mechanism? All right, and so, but it's not enough to be just an academic pursuit. It has to be in the real world. All right, so yes, green chemistry has to have some sustainability benefit, but that's not enough. It also has to have good performance. No one's going to buy a cleaner that doesn't clean. No one is going to buy a vehicle that doesn't drive. We have to have excellent performance, and it has to have the right cost. It can't be just wealthy people can afford it. It has to be affordable, and it has to succeed in the market. So for something to be green chemistry, it has to have better performance, better cost, and oh, by the way, also more sustainable. Then you have green chemistry. When someone comes to me and says, you know, John, we have to work hard. It's not just green chemistry. It has to have good performance and good cost. I go, they didn't read the book. That's the whole point of green chemistry. Is how we do that. And who's the only person who can do this? The person who invents it. Because after it's invented, you can't change how it's done. And so this is about invention. So I would argue the biggest barrier to sustainability is not the desire, it's the invention itself. Because if you invent something that works better, costs better, who's not going to want it? All right? And so I left Polaroid at this moment when I realized this. The height of my industrial career, I left and I went to academia. I became full tenured professor of chemistry, full tenured professor of plastics engineering, and I started the world's first PhD program in green chemistry in 2001. It has everything in a regular chemistry program, so I don't remove anything, but I added a one-semester course in mechanistic toxicology, added a one-semester course in environmental mechanisms, added a one-semester course in law and policy. Because what you find is when people invent technologies, the biggest reason that it doesn't make it to the real world is because of those things. All right? And so essentially, the way I look at it, let's imagine tomorrow morning, everyone in the world wakes up and says, I get it. I will only buy sustainable products. Every store says we will only sell sustainable products. Every manufacturer says we will only manufacture sustainable products. We're in trouble. Because for my estimation, only about 10% of the things, the ceiling tiles, the carpeting, the clothing, the electronics, the medicines, only about 10% are truly sustainable. 90% of the technologies still have problems. There's some easy things that we've been doing over the last 10 years, so maybe that goes up to 20%. But right now, in 2024, I would argue about 80% of the technologies haven't been invented yet. This isn't industry saying, we're making a lot of money doing this, never mind. Better performance, better cost, oh, by the way, better for humans and the environment. Who wouldn't want it? So from my perspective, this is, so why do I fly from Boston to Santiago to talk about this? Because I hope I'm looking at people right now, and someone in this room is going to turn a traditional technology into a green chemistry technology. And because you've poured beakers and flasks or done something in the lab, hundreds of thousands of people you will never meet will no longer be exposed to hazardous materials because you got it right. The world needs you to do this. But you can't do it if you don't have the skills. You can't do it just by wanting to. You need to understand what are the chemical mechanisms that I need to avoid so that I can do this. And if your education isn't teaching you, and now, University of Santiago de Chile has signed the Green Chemistry Commitment. You are leading the world in doing this. All right? And it's not the birth of ethics. It's not like people didn't care in the past. You know, when I was a music major, I asked a chemistry professor, if I become a chemist, will I put myself and my future family at risk? I actually had the clairvoyance to ask that question. But you know what the professor said to me? He says, well, you know, if you're asking that question, maybe you shouldn't be a chemist. So I didn't for 20 years, okay? But it's not that I was a bad person. What people say is chemistry has to be toxic. Do this experiment. I love to do this. If I go to a group of chemists and I say, oh, yesterday I was working with hydrogen cyanide. I was scared. That was dangerous. Just wait. What? Oh, yeah? Well, once I worked with phosgene, you know, that's much more toxic. Oh, yeah? Well, once I worked with this explosive that could take away, and we brag about how we work with dangerous things. It's almost like it's cool, you know, that we work with dangerous things. But it's okay, because we wear gloves to protect our skin. We wear masks to protect we wear goggles to protect our eyes. We install scrubbers and filters and smokestacks to protect the air, the land, and sea. That first slide that I showed you of all those disasters, they had these things, but something went wrong. And so the problem is when you look, risk has two components. It has the exposure, and that's what we've been doing for 100 years. That Herculean giants, people in engineering have learned how to control exposure. And we protect humans in the environment by exposure. But A, it's very expensive. B, inevitably something goes wrong. So, the revolution that is green chemistry is another part of risk. The actual intrinsic hazard. If I look at a molecule, say I make a red dye, and I want to know the structure of a red dye. Well, I need an electron donating group, an electron withdrawing group. I need to have enough double bonds in conjugation. Okay, that'll make it red. I need it to stick to a fabric. Well, I understand hydrogen bonding and van der Waals interactions. I need it not to fade in the light. Okay, I understand redox properties. And, oh, I don't want it to be a carcinogen. What makes something a carcinogen? If I don't know what makes something a carcinogen, how am I going to make a molecule not be a carcinogen? And so if I do learn what makes a molecule cut, I just add that to the list. I want it to stick to a fabric. I want it to not fade in the sun. Oh, by the way, I don't want it to be toxic. Okay, and that's the dream of green chemistry. We can't snap our fingers and have everything be green tomorrow. We've been inventing stuff over 200 years. Green chemistry's just been around for a short period of time. It's going to take 40, 50 years to truly make these changes. We're going to have to be patient. But we got to dedicate ourselves to making it happen. All right? And industry, it's interesting, when my book came out, Dow, 3M, Merck, Pfizer, all the companies started green chemistry programs. Most companies now have vice presidents of green chemistry programs, because it just makes smart business sense. If you have a technology that is safe and non-toxic, and you have a technology that is toxic and regulated, it costs so much less to store. It costs so much less to transport. All these things, it's just so much easier if it's non-toxic and non-regulated. This last one, I think, is the most important, though. Okay? It's interesting. One of my students gave a presentation at the National Academy of Sciences in Washington, D.C., and she made this low-temperature semiconductor out of titanium dioxide. She gives the presentation. There's about 300-400 people in the audience, and they all applaud. And at the end, you know, some person from the audience gets up and says, "Excuse me, ma'am, but aren't you concerned that associating yourself with this green chemistry will limit your job opportunities?" Okay. She had about 6 job offers in her pocket at this point. She looks at the guy and she goes, "Dude, why would I want to work at a company that didn't want me doing green chemistry?" And the guy goes, "Oh, you silly person." At which point, about 150 graduate students got up and gave a standing ovation. If there's ever a book, if there's ever a movie, that's the closing scene. I passionately believe the next generation of students get this. We need to give them the skills to do it, but there's no question here. They get it. And so that green chemistry PhD program, over 12 years, had about 150 students go through that program at different levels. The average time it took a student to get a job, 2 days. The longest any student spent looking for a job was 2 weeks because she turned down her first 6 job offers. I've been out of academia for almost 15 years. I still get emails and phone calls from companies. John, do you have anyone graduating? Because all universities, we really, across the world, kind of teach the same thing. We're all using the same textbooks. We all read the same journals. So everyone is kind of the same. There's no real difference, to be honest with you. But the biggest problem in industry is understanding toxicity. And there's so few. Anyone that is a good chemist, you can't not be a good chemist. But to also know something about regulations and toxicity, industry really needs that. The reason that it's not a big thing is because most universities still don't teach it. All right? And so the way I look at it, there's so many approaches. There's all these different approaches: responsible care, systems thinking, limits to growth, UN SDGs, circular economy. There's so many books that people are writing, doing this thing. And what makes me really sad is we're in this polarized, competitive society where someone will say, oh, well, this is the correct way to do it, and no, this is not the correct way, and this is better, and this is not better. And really? All of these approaches are wonderful. All of these approaches are important. And if somebody wakes up in the morning and says, I like this book, I want to spend my time using this, instead of telling them why, well, actually, this would be better, what we need to do is embrace one another and say, how can we help each other? How can we collaborate to just, if everyone's passionate doing what they love, then we can start solving problems. But the thing with green chemistry is that when people say to me, chemistry is a mature science, I laugh. I actually feel chemistry is just on the verge of so many amazing things. There's no better time in history to be a chemist than now, because as we learn more, we're going to do. So all those approaches that I talked about there, what they are people saying, well, what would we like chemistry to be? So maybe they call it sustainable chemistry, or clean chemistry, a circular chemistry, a safe chemistry, a regenerative, all these different approaches. Notice I don't put green chemistry on this list. All right? The way I look at it is all of these approaches, whatever they are really talking about how do we measure, how do we monitor, how do we characterize. It's telling us how do we want to describe it. But it's not telling us how to do it. It's telling us what to do. And shouting at someone, you should make something non-toxic, you should make something better for the environment, doesn't make them do that. You need to tell them how. And that's where green chemistry comes in. So green chemistry isn't another one of those, but seeks to change the shape of chemistry so that everything we do one day goes to whatever you want to call it. But to do this, Einstein said no problem can be solved at the same level of awareness that created it. We need new eyes, new ideas, people who normally wouldn't have gone into chemistry or wouldn't have had an opportunity to be inventing on the global scale. We need different people. If all we do now is give grants to everyone that's been getting grants for the last 50 years, they're going to keep doing the same thing. We need innovative people who want to be different, who see the world in a different way. I would argue that the absence of this inclusion is why we need sustainability now. I would say 50 years ago, if there was someone saying, what, you're going to use what molecule to do what? Maybe we would have done better. But because we have such a closed society in chemistry and material science, we don't have people looking with the right eyes. This is desperate. We need this, okay? And so I look at it as a toolbox, and in the toolbox of chemistry, there's a drawer for carbon bond forming reactions, oxidations, reductions, hydroxylations. This toolbox is full. If we can conceive of a molecule and it doesn't violate some fundamental physical laws, we can probably make it. But if we imagine a green chemistry toolbox, I told you this is 90% empty. I believe a smart individual, a smart company, will open the green chemistry toolbox first. Better performance, better cost, who wouldn't want that? But 9 times out of 10, it'll be empty. Then what do? The mistake people think is industry no longer has the luxury that they can just invent something. They can't say, stop everything, let's invent. They've got to hurry up, get something done by the next quarter or something like that. So they close the green chemistry toolbox, they open the traditional one, say, what is it going to cost for the gloves and the masks and the goggles? And they just keep going. So we need to have an army of people dedicated to putting tools in that green chemistry toolbox. And again, I hope I'm looking at a group of people today that someday their name is on one of these draws because the world needs to. Okay? So here I am in academia now, and I'm called the United States #1 science professor, and I spent a half an hour in the Oval Office with him. Get a couple glasses of wine in me, and I'll tell you more about that someday. But here I am at the top of this thing, and I resigned from academia. I left academia. Why? Well, at this point, because I'm an interesting speaker and I have interesting thoughts, every journalist, every magazine, whenever there's something in sustainability, someone asks me for a quote. John, what do you think about this? And so when Canada banned Nalgene plastic bottles because of bisphenol A, they asked me for a comment. So I'm driving in my automobile, and I get my phone call, because I'm a good citizen, I pull into a parking lot, and I'm talking on the phone, and it's a grocery store. And while I'm talking on the phone, a pregnant woman comes out of the grocery store. She's stumbling with her keys, stumbling with her bags, and she puts her cash register sheet in her mouth. And I'm watching this, and a nerve just explodes in my head. And I go, you know what drives me crazy? What drives me crazy is a polycarbonate plastic has femtogram quantities of bisphenol A that are leaching out at a tiny bit. But a thermal cash register receipt has milligram quantities of bisphenol A. Holding on to a cash register receipt for 30 seconds, you will have more body exposure to bisphenol A than a lifetime of drinking out of plastic bottles. Yes, it's important, but why aren't we talking? And they go, John, calm down, this is about plastic bottles. But they mention it. John Warner reveals bisphenol A. I didn't reveal anything, it was there. Next thing you know, thousands of websites. John Warner reveals bisphenol A in thermal cash register. The #1 NPR National Public Radio show is called On Point with Tom Ashford. I'm a guest on that twice. John Warner reveals bisphenol A. In fact, in this world-class journal, on the same page as a cat pushing a shopping carriage, John Warner reveals bisphenol A. I'm looking at this cat, and I'm saying, something has gone wrong in my life, all right? I've spent my life inventing things that are better for humans and the environment. No one cares. Never got a story about that. But the one time by mistake I mention a problem, now I'm famous. And I thought, hey, isn't that interesting? Our society loves the people who identify the problem, but they lose patience when it comes to the people solving the problem. And it's all boiled into how funding and grants. I said, I don't want to do this anymore. And so I left and started my own research institute. And it was the Warner Babcock Institute. Now it's evolved. And if I'm going to do this, if I am working in academia in the state of Massachusetts, a full tenured professor, I can't have a salary reduction. I can commit crimes, do all kinds of things, and they can't even change my salary. So I'm pretty safe. So if I'm telling industry, you should do green chemistry, they say, well, wait a minute, what risk are you taking? And so by leaving that and putting my family, my everything, and saying, okay, I mean this. We have to be successful. This has to work in the real world. And so I started to just invent. And using the principles of green chemistry, over the next 14 years, published 357 patents, all right? Spun out 6 companies, licensed over 30 technologies to multinationals. This works. I don't think I'm some genius. I think using green chemistry facilitates the process. Okay, so I want to end by giving you a couple examples. What does green chemistry look like to someone working in the lab? Okay, so my first example is one day I'm considering insect sclerotization. It's the process by when a bug sheds its exoskeleton, over the course of a couple hours, it turns hard and black. I'm going, huh, there's something in nature that goes from white to black. People color their hair when they go gray, but they use really toxic, nasty stuff. So I looked at this as a terracinase oxidative cascade. So I said, all right, I didn't want to grind up dead bugs. I thought that was nasty. And so instead, I found this bean called velvet bean. I extracted and made an iron and a manganese catalyst, and all food grade material, took all things that one would put in food, made a formulation, bought a bunch of gray hair, and it worked. It's permanent. It doesn't fade. It doesn't wash. But it's not painting the hair. It's restoring the hair to an original color. This is going to be hard for you to believe, but if you look really closely, I have a couple gray hairs, okay? And so if I put this in my head, it goes back to the color my hair was 30 years ago. My friend with black hair, it goes black. It's my hair, brown hair, it goes black. The same chemistry, I've realized that the protein in our hair template the three-dimensional packing of these pigment materials. And if I can very gently allow that stuff to penetrate the hair, it restores the human thing. So filed a bunch of patents in the same way that we have a fingerprint. Our hair has a hairprint. And for the last 8 years, this has been a company. You can go online and buy hairprint. You know, there's myhairprint.com. If you act quickly, they'll throw in a set of knives. But this thing has been going for 9 years, and it's just growing, growing. I would not have been able to invent this was it not for the principles of green chemistry. From an idea in my head to starting this company was about 19 months, 20 months. Okay. Next example, this molecule here is called copper ATSM. It is insoluble brick dust. It is just doesn't dissolve. But if you put surfactants in DMSO and you put it with laboratory animals, it has really good neurological behavior, especially for ALS. So I took my non-covalent derivatization and I came up with a form where I made it orally bioavailable, customized it crossing the blood-brain barrier, and using mechanochemistry manufactured it, started a pharmaceutical company, phase 1, phase 2, phase 3 clinical trials. It's now looking like one of the most promising cures for ALS. Still a long way to go, but I would not have been able to do this without using the principles of green chemistry. Another example is asphalt pavement. There are hundreds of millions of miles of asphalt pavement in the world. The sun and the air oxidize the surface, making it brittle and hard. And so every year we repave about 10% of all the roads. So 10% of the roads gets repaved all year. But because it's brittle and oxidized and hard, we throw away the stuff that we dig up, and then we use new petroleum and new aggregate to make the new road. I said, but could I come up with a catalyst to instead recover that and use that same material and have a truck that comes and digs up the road, processes it, and just pave it? And so if I'm willing to put stuff in my hair, I'm willing to dig up my driveway. So this is my home in Massachusetts, okay, in 2013. It was a very cold day. And so the work is I dug up my driveway, went to the plant, climbed up a ladder, put my catalyst in. The workers came with a truck, came back, and they were laughing at me. They were saying, John, you're an idiot. It's way too cold to pave. You're using too much recycled material. We're going to put a big hockey puck on your front lawn and drive away. I actually had someone from the government there, from the Massachusetts Department of Transportation, with a clipboard. I said, okay, go ahead, do it. And they open up the thing, it comes out like sand, and they scream like school children. It worked better than industry standard. It actually performs better. No new material, 100% recycled, just with a catalyst. Think of the cost savings, not buying any materials. And so started a company called Collaborative Aggregates, non-covalent interactions, molecules collaborating. I wanted to call it entropy mix, and the people said, oh, that's a terrible name. So I said, how about Delta S? They, okay, so don't tell them Delta S again. Anyway, so that's the catalyst, and then started a company called Delta Mist, which is the spray coat to preserve. Idea in my head to starting this company was 18 months. People say, oh, it takes 10 years. I don't think so. With green chemistry, the time to market is so much more accelerated. All right. Another example, this is one of my favorite M.C. Escher drawings. You see the birds in the sky and the fish. And it's kind of hard. When do the birds stop being birds? When do the fish stop being fish? In biology, many transitions are like this. It's not discrete, but it's subtle. So I said, could I take a hint from nature and design a semiconductor that slowly turned into a chromophore, and have the chromophore slowly turn into an electrolyte? And I started making photovoltaic devices. It turns out it is the highest efficiency photovoltaic device in history. All right, and it works so good that it works indoor with just very low light. All right, and so started a company called Ambient Photonics, and Amazon, the company Amazon, last year invested $100 million, and we're in manufacturing in California for a technology that for anything in the fire detectors, smoke detectors, anything that uses a battery, you don't change the battery, you keep charging the battery with ambient photons of light. I would not have been able to do this without using the principles of green chemistry. And the last example is, the glasses that you go outside, they turn dark, and you go inside, they turn clear. I changed the chemistry a little bit so that it goes from hydrophilic to hydrophobic. If I make a super hydrophilic material, it sucks water, but now you need a lot of energy to get that water out. But if I can make it so that, imagine, this is an oversimplification, but imagine I have an umbrella over on a rowboat in the ocean. The sun comes up, and water absorbs on the underside of the umbrella. When the sun goes down, it rains pure water in the rowboat, and I can take that out and cycle it back and forth. I designed the chemistry so that it works now in the nanosecond time frame. So in the shadow of a windmill, you get a film that capture, release, and so the water just pours off the film, capture, release by the light going on and off. This couldn't, so I started a company called Mist Miner, and this could not have been done if I didn't embrace the principles of green chemistry. All right, so my closing thought, this is a science talk, this is a history talk, but this is also a love story, all right, that this is what's really driving me crazy. How are we gonna do this? How are we gonna invent these things? So meet my wife, Dr. Amy Cannon. She and I in 2007 left, she was also a professor. I started my research institute. She started Beyond Benign. And she does the education, I do the invention, and we have Juliana here. This is, in my opinion, the most important thing we do, because we need armies of people that don't want to make sustainable products. Everybody wants it, but everybody knows how, and gives people the skill. So the most important thing, so I don't want to tell people, oh, the world is terrible, everybody's dying, everything is bad. I want to show, look at, using green chemistry, we get better products that are more profitable, that are faster. It's not a compromise. We can have things that are good for the world and still make a good economy, all right? And so the most important thing is to teach people. So Beyond Benign has the green chemistry commitment. And there are now almost 170 universities globally that have signed this commitment. And I am so proud to see one of these logos up there. We just need a lot more of them, okay? And so I am so appreciative of what people in this room are doing for green chemistry. Thank you for giving me the time to share some of my thoughts with you. And I just can't wait to see the amazing things that come out of here in the next few years. So thank you very much.
Thank you very much. We have time for questions. Si alguien quiere preguntar algo, si lo pregunta en español, está bien, ahí lo tratamos de traducir. Preguntas para el profesor. No tengan miedo. ¿No? Yo quiero. Dale, ahí vamos a ver cómo lo traducimos.
¿Cómo aborda la química verde aquellas experimentaciones donde todavía no se ha podido sustituir reactivos que son tóxicos ¿Qué papel juega la química verde allí? Hace poco estuve conversando con un compañero y no pudo realizar una reacción sin tolueno y sin algunos reactivos que necesariamente eran tóxicos para que le dé los resultados que estaba buscando. Entonces él buscaba la forma de utilizar química verde, pero le resultaba mucho más engorroso todo el trabajo de investigación para poder llegar a sus mismos resultados. Entonces, ¿cuál es el enfoque de la química verde en esos casos?
¿Lo quieres traducir o traducir? Es más fácil a ti o qué?
I like your hat.
He wants to know how you're going to take the challenge trying to do chemistry, but without using the regular compounds. And it's already a difficult job to do, so how do you
So, again, the thing is that, as I said, 80% of the things we haven't invented an alternative. We can't snap our fingers and tomorrow do that. Right now, there are many applications that need PVC. Right now, there are many applications that need some toxic intermediates. And that we will need them forever unless someone invents something else. And so it's not today we must stop because we need to invent them. But I would argue there is not one thing that there isn't a brilliant person, not me, but somebody will come up with these alternatives over the next 10, 20 years. And so we just have, how does green chemistry look in my lab? If someone works in my lab, this is what happens. My lab looks like every other lab. We wear the masks and the goggles. You know, people come and expect everyone to be wearing robes and slippers and smoking pot. But it's in the regular lab. We got all the toxic materials, the hazardous materials. So what happens is when we do a reaction for the first time, let's say we're going to synthesize ammonia, and we have a journal article, and we're going to repeat that article. In the laboratory notebook, we write the numbers 1 through 12. And we ask ourselves, okay, this article was written 10 years ago. They're using benzene as a solvent. Well, we know toluene works just as good as benzene, but is not carcinogenic. Okay, well, maybe we should use benzene instead. Oh, they're using all this energy. Wait a minute. A lot of journals say heat at reflux, okay? No one has thought, do we really need that temperature? What if we reduce the temperature we're using? And so it's just ask the questions. Is there something obvious that I can do? And maybe 10, 15% of the time, there's going to be something obvious. But then there's going to be things, well, I don't know. Maybe this will work. Then we talk. I'm the boss. I have to say, gee, we have a deadline. Should we try that? And usually I'm going to say, yes, let's try it. Because if we can make it more green, that's great. But then there are going to be things that we are stuck. We have to use. I have to use iodomethane. I have to use this reagent. I have to use this. Then we ask ourselves, if we have to use this, do we have the right gloves? Do we have the right masks? Do we have the procedures in place? How can we do this to make sure that I'm safe, the people around me are safe, and then we turn the page and behave just like any other chemist. So it's just that conscious effort at the beginning to ask yourself, am I just a mindless robot reading a paper and doing it? Or am I going to use my skill in chemistry to question these things and maybe change some of the procedure to make it better for the world? That's it.
Thank you.
He touched a problem that we face, all students face, because they have to finish the job, you know, and the time we need to make the changes. Sometimes it's a limitation.
Oh, and my humble response to this, okay, 370 patents, 6 companies, 30 technologies. I don't feel I'm going slow, and I do green chemistry. So someone who says green chemistry slows you down, they don't know what green chemistry is. Okay, because I think green chemistry speeds you up. Okay, I really do.
Thank you.
For example, how we do with the industry. Because, for example, I am trying to produce nanomaterials using a environmental friendly process, but it's expensive than the conventional.
Yeah.
and the industry are not interested in my I don't know in my process. You know, so it's how we can manage that.
Yeah.
How we can convince the
So,
industry.
in a different lecture, I talked a lot about this, all right? That 30 years ago, academia did a lot of research and a little bit of development. And industry did a little bit of research and a lot of development, and there was an overlap. And it was very easy to take something from academia to industry. But over the last 20 years, academia has changed. Now it's all about impact factor. How many journals do you publish in? Someone publishing 5 papers, and now people publish 100 papers a year, and you can't do deep development. So academia has done less and less and less development and is more research. At the same time, industry has done less and less research, and so now there's a gap, and that gap is very difficult. Very few companies, the concept called organic growth. Organic growth is how many products invent themselves and manufacture. How many products does Procter & Gamble invent? How many products does Natura invent? And what you'll find is almost none. Everything they do now is they acquire from other technologies because they don't have that fundamental research. And it used to be academia, but because academia is worried more about publishing papers and high impact factors. So I feel now we need more than ever entrepreneurs. People who take the risk, start a small company, take the best of academia, take the best of industry, and bridge that gap. Now, I'm not saying everybody should become an entrepreneur, but everyone in academia should learn to talk to people who are entrepreneurs. Everyone in industry should learn to talk to people as entrepreneurs, because that now in 2024, there's too much of a jump from academia to industry. So at the very moment we need new technologies to make it to the real world, it's become harder and harder because of how academia and industry has evolved. And so it doesn't mean everyone has to start a company, but learn how to talk to these people. So the interesting thing, what I have learned, is that if I go to Procter & Gamble and I say, I have this mechanism that colors hair, it goes to the scientist. And the scientists say, well, wait a minute, that's my job to invent this. And it's very unlikely they're going to be interested. But if I call it hairprint, and I say, I have a product called hairprint, I've done nothing else, I've just named it. It's the same technology, but instead of calling it a chemistry, I call it a product. Now it goes to the business development people who want and need those new products, and they will listen. But if a chemist goes to the chemistry part of an industry, you're competing with them, and they want to get raises, they want to get promotions, they don't want to say your stuff is good. But the business people, they're going to want it. So get it to the point where it looks more like a product and less like a science experiment, then it'll happen. And all that takes is get a website and call it something. As simple as that is, and we need to learn to communicate. Because in my experience, the things don't succeed. It's never because of the technology. It's never because of the market. It's because people didn't communicate well. And so many times, big companies fail, not because they didn't do the right thing, they just didn't talk to each other the right way. We need to learn to talk to the entrepreneurs and talk to the industry people so that we're not wasting. Right now, 95% of invested technologies never see the real world. Only 5% of money that goes into research ever sees the real world. And we're talking about how do we get more things in. I think we got to do better and make that 5% go up to 90%, because the world needs us to be better. And so that, when we look at this, is the goal to, once it's in a paper, you're done? Or do you want to get out of the publication into the real world? We need those skills.
Another question?
Thank you very much for your presentation. My question is, what is your opinion about nanomaterials and synthesis and waste?
Okay, so nanomaterials are an amazing frontier still, even though they've been around for a long time. My concern with nanomaterials is that if you're a good toxicologist and you do a really good study and you take the nanomaterials, very, very pure nanomaterials, and you look at the toxicity of the nanomaterials, you'll find they're not toxic. But what the nanomaterials actually do is they change the transport of molecules across cell membranes. And so it's not the nanomaterial, it opens the door for something else that normally doesn't get into the cell. So if you're in a factory that's been working with non-toxic material because it's not bioavailable, and all of a sudden you bring in a nanomaterial, what happens is the thing that was safe is now toxic because the nanomaterial is helping it go in. Now, it's not a lot. These are very small examples, so the majority of things, but there's enough. So in Europe, European companies, the insurance agencies will not underwrite products that have nanotechnology in the cosmetics, okay? I think that's an overreaction because I think that nanomaterials are still amazing. But we need to be cautious and be honest and understand better what's happening with them. But I myself, a lot of the work that I do is in nanomaterials. The other thing is the language, the communication. What do we really mean when we say nanomaterial? This is, I apologize, I'm sure everybody understands this, but if I take a piece of metal and I do all the physical and chemical properties, if I cut that metal in half, it's still going to have the same boiling point, melting point, electrical conductivity. If I cut that in half again, it'll still have the same. If I cut it again, it'll have the same. If I cut it again, it'll have the same. At some point when I cut it in half, things change. That is what a nanomaterial is. A nanomaterial is defined by changing that nonlinearity of product performance because of the dimension of size. It's not just something that's smaller. And so those are the things that are so exciting for quantum computing, for pharmaceuticals, for so many things that with the nanoparticles, but it's when we truly have changed the dimensionality of particles together. That's where the cool things happen. We're just on the beginning of amazing things. And interestingly enough, if you look inside a cell, everything in a cell is a nanomaterial, all right? And so biology has been doing nanochemistry for 3.8 billion years. So we need humility to see how nature is doing it, but it's exciting, and I think it's super important. There's a lot of problems that can be solved, especially in energy. I think in energy, most new energy forms will have some aspect of nanotechnology.
We have time for more questions.
Thank you so much for such a wholesome and compelling talk. I wanted to ask you about, because I'm just starting in science, so what advice would you give to someone who's just starting as a PhD student in green chemistry?
First, thank you. The world needs you. And you are going to have bad days, and you're going to have good days. Okay? The thing to remember, and again, this is just, I'm being very philosophical here, but there are so many things in all of our lives. There are so many things that we do, okay? If I wanted to look at all the bad things that happen in my life, every day there's some bad things that happen. If I just focus on those bad things, I can say, oh my God, my life is terrible. If I look at all the good things, I say, oh my God, my life is amazing. It's not changing the world, it's just what I choose to look at. And so when we have a bad day, realize we're making a decision to weigh those things one. And as you become a chemist, it's going to be difficult days. And my first advice is just don't let that get you down. Find what you, and for green chemistry, what you want to do is, what do you love? Do you want to do cosmetics? Do you want to do forestry products? Do you want to do nanotechnology? Find some traditional chemistry that you love and become expert at that. and bring green chemistry to that field. And so always have the traditional thing, and then bring that green chemistry in. So don't look for places that are already doing green chemistry. You bring green chemistry. Be that change person that brings green chemistry. So it's too early. There's not enough people in the world doing green chemistry. If you just go hang around everyone that's doing green chemistry, then the world isn't benefiting from the change that you can have. So every once in a while, go and talk to people that aren't doing it and see if you can make them change. But first and foremost, just making that decision is precious.
Anyone have?
Do you have this one here? Right here?
I'm curious, John, if you could speak to the disciplinary inspiration that can be drawn from, say, disciplines that are outside of chemistry. So when you gave the example of the bug, for instance, that's a very striking example of looking outside of the traditional methods. So I was curious if you could speak to the kind of biomimetic approach to looking at nature or biology or any of the other inspirations.
So my philosophy is that innovation doesn't happen at the focal point. The harder you stare at something, the less likely you will innovate. But the innovation happens in the periphery. So using any analogy will put what you're doing in the periphery. So one example I have, I actually give creativity classes at art museums. And I'll take a piano up and I'll play a diminished seventh chord, which is a very tense chord. Then I'll play a major seventh chord and it goes, and I say, if I just played the major seventh chord, it'd be boring. The reason you liked the major seventh chord is because I created this tension. If you listen to any music, especially movies and soundtracks, you'll hear that minutes before some big scene happens, there's tension in the music preparing you for that. Then I take a reaction coordinate diagram and talk about energies of activation, saying every chemical reaction starts with tension and then is released. When we think about music and impose that on molecularity, interesting things can happen. Another example, my father-in-law is what you would call a football coach at soccer. Okay? And he was on the U.S. Olympic team on the second level, not the high level. And one day he's going, what do you do, John? I say, okay, draw a soccer play for me, a football play. He has the goaltender, he has this, and then I take that thing and I go, okay, well here's a molecule with 3 hydroxy groups. Here is a molecule that I want to react with, but I only react it with this one and not with this one. And so what I need to do is have a protecting group over here, and then take its play. I go, okay, so you have the defenders over here, you have the person kicking the ball over here, you get the goaltender. So who would have thought that designing a play on a soccer field, on a football field, has some similarities to how we design chemistry. Taking biology is so much easier because biology works with molecules, but it doesn't have to be just biology, it's just getting your head to turn a little bit there so what you're really looking at goes a little bit to the side. That's where creativity is. And so that's why talking to different people, going to different conferences, almost everything, every one of my inventions has happened doing something entirely different and letting the mind wander. And so I think that's a super important part of creativity and innovation. Thank you for the question.
We could have it.
Good morning, I'm sorry, am I speaking English? And in the question to be or not to be, we have the question of we use hazard material or not we use, or we use hazard materials and responsibility, security, sustainability, and responsible care. No sé si quería aclarar la pregunta.
No, parece que no.
Ok. Cuando no usamos productos peligrosos.
No los usan. Ajá.
O los usamos responsablemente,
Ah,
sustentablemente.
esa es la relación de riesgo y...
Claro, o no los usamos o los usamos responsablemente para poder avanzar en ello.
He asked if, I'm asking for advice. He's asking if we should use hazardous compounds with responsibility in order to advance in chemistry, or not use hazardous materials.
So first of all, I would not be so presumptuous to say I have any right to say what people should do or not do. There are things that we need to use hazardous materials, and we need responsible care, and we need wonderful companies that have embraced responsible care, but not forever. We also want to be committed to imagine the day when we don't have that hazardous material. And so it's really, so the way I look at it is there are so many aspects of sustainability. We need political people, we need business people, we need sociological people. There's all these people that have a piece to play. But to me, you know, people talk about you should be the best you should be. I don't believe that you should be the best you should be. That's important. But what is more important is to look in the mirror and say, what can I do that other people can't do? Chemists do chemistry. If we turn into politics, if we turn into management, we're not giving the world our skills to invent. So it's not to say all that other stuff isn't important, but there are people doing that. Chemists need to invent new chemistry to help the people that are trying to do that. So responsible care will be here forever. I don't believe there's ever a day when everything is perfect, because we will discover things we thought was safe were actually hazardous, so that's going to keep changing too. So we have to be committed to always doing the best we can, inventing the better technologies, and when we don't have them, doing them responsibly. And the thing is to never say, I'm done. We will always have this material. To always be saying, we need a different material, but until we have that different material, we're going to have to do the best we can.
Sorry, we are out of time. So thank you very much.
My email is here. If you think of any questions, please feel free to send me an email. Happy to speak with you by email. But thank you so much.